as an additional example, let's also consider the improved version of the Malthusian model, that is the Malthusian model with logistic, or with competition, as we have called it. That, as we saw, was given by an equation of this form. It was x dot equal to ax minus this additional competition term. So this competition term that was quadratic. And of course, this is a differential equation. We are going to assume that there is an initial condition so that we can solve it. And what we are going to do is simply to find the solution of this differential equation. Is this a state representation? Yes, x is going to be our state, and we are writing this in the form of x dot equal to a function of time, the state, and the input. There is no input now in this model either, so this is again an isolated model. Isolated system, because there is no input. Once again, we are just observing the population grow or decrease. Can we write this as an input output representation? Of course not, I was about to say, because there is no input. But if we call x, y as our output, and we write and we put we have already this explicit output representation. So what I'm going to say here, just summarizing as an observation, the equation is in a state space representation if we write y equal to x as its output, we get an explicit input output representation. That is y dot equal to ay minus by square. Why have I put this in quotes, the input part? Because there is no actual input. So the input output representation is not very interesting. What is interesting though is the way we are going to solve this, because the solution of the Malthusian model without competition was actually quite easy, and you'll see that just by adding a term that looks very innocuous, like this quadratic term, makes the solution a little more complicated. So in order to proceed for the solution, we go on as usual. So first what I do is I write, instead of x dot, I to use the notation dx divided by t, and this is going to be equal to a minus bx times x. So we can write this in this way. It's exactly the same expression. And one thing that I try to do when possible is to see if I can write an expression where all that depends on x is on the left hand side, and all that depends on t is on the right hand side. It seems that that can be done because I can write this as dx divided by a minus bx x equal to dt. So I have separation of variables, and now I could proceed and integrate both sides. On the left hand side I have a fraction of two polynomials. At the numerator I have 1, at the denominator I have this second order polynomial, so in theory I know how to integrate this, and the right hand side is just a constant, so it's not too bad. Since I want to make the integration easier, I manipulate this left hand side a little better. So what I'm going to do is I'm going to multiply both sides by a. Why not? So that my expression becomes this. Then what I'm going to do is on the left hand side at the numerator I'm going to subtract I have written this expression wrongly. I'm going to subtract and add the term bx like this. So if I write the numerator as a minus bx plus bx, I still have a. The denominator is given by a minus bx times x as usual. And since I haven't done anything on the left hand side after all, the right hand side stays the same. Now this expression here allows to write this ratio of two polynomials in a better way, because if I take a minus bx divided by the denominator, I simply get 1 divided by x. And if I take plus bx and I divide that by the denominator, the two x's cancel out, and so I'm left with a b divided by a minus bx. All this in the x equal to a dt. So now it's clear what I have done. I have simply found a way to decompose this ratio of two polynomials in simpler terms, because now I know how to integrate 1 divided by x, and I also know how to integrate 1 divided by a minus b, b divided by a minus bx. Now what I'm going to do is just to make this expression look a little prettier, just a bit, so that I can really integrate without making any mistakes. So I divide both terms of this fraction where the term b appears. I divide that by b, both numerator and denominator, so that I get something that looks like this: 1 divided by a divided by b minus x. This is going to be very easy to integrate now. Dx equal to a dt. Now the next step is actually to integrate from 0 to t. What I mean by integrating from 0 to t is that I'm going to integrate the left hand side from x at time 0 till x at time t, and the right hand side from t equal to 0 till t equal to t. So when I take when I'm integrating, I find that the integral of 1 by x is given by x of t divided by x of 0. This term is analogous to the term that we found when we were integrating the Mathus term. When I'm integrating this other term, that when b goes to 0, this term tends to 0, so it was not present in the simple Mathus model, but now it's here. I get that this term is given by minus the logarithm of, and here I have a divided by b minus x of t divided by a divided by b minus x in 0. This quantity here is equal, must be equal to the integral of a from t equal to 0 till t, so it's simply a times t. So I have this expression here. Next step is to put everything in a big logarithm so that I can exponentiate. So I have x of t, and I also like to keep things that depend on t on one fraction, and things that instead depend on x at time 0 on the other side, so that I have already separated the initial condition, what depends on initial condition, to my actual x of t. And this is going to be equal to at. If I take the exponential, I find that x of t divided by a divided by b minus x of t times a divided by b minus x of 0, that is divided by x0, needs to be equal to the exponential of at. Now what I'd like to do is to solve with respect to x of t. So this is it's not going to be difficult at all. We just need to be smart. Let's take the inverse of this. Well, let's do this. Let's write this in the following way. First, x of t divided by a minus b minus x of t is going to be equal to x of 0 divided by a divided by b minus x0 for exponential of at. And this is totally okay. The only thing I want to solve with respect to x of t, we can do a smart thing. That is, let's flip this fraction here. So we write that as a divided by b minus xt divided by xt equal to, needs to be equal to the inverse of this fraction as well. A divided by b minus x0 divided by x0 times the inverse of exponential of at is exponential of minus at. Here we are. Now it becomes easy because this becomes a divided by b times 1 x of t minus 1 equal to a divided by b 1 divided by x0 minus 1, and all this multiplies exponential of minus 80. Let's move the 1 on the other side. So we have a divided by b, and the x of t is here, equal to, and now we write this as 1 plus a divided by b 1 divided by x0 minus 1, all this multiplying exponential of minus 80. And here we are. Now we can flip the fraction again, and so we can write that x of t needs to be equal to b divided by a. Let's go with all the steps. Let's try to avoid mistakes, because I think that this could have been actually an easy mistake. So we take the inverse of this fraction here, we take the inverse of this fraction as well, so this becomes 1 plus a divided by b 1 divided by x0 minus 1 exponential of minus 80. So we have taken the inverse of this, and after this we multiply by a divided by b, and we have our solution. X of t is going to be given by a divided by b, that divides 1 plus a plus b 1 divided by x0 minus 1, that multiplies the exponential of minus 80. We can multiply both terms by b divided by a. It's not that we are going to make this much nicer, but we can have maybe an expression that is a little lighter, that looks like this. B divided by a, and inside here we have 1 divided by x0 minus b divided by a exponential of minus 80. Here we are. And so as a check, as a test to see if this expression is correct, as an observation. Let's verify that for b that goes to 0 we get the Mathus solution. So for b that goes to 0 we get that x of t is equal to, and now let's make b go to 0. This fraction goes to 0, this other fraction goes to 0, so we are left with 1 divided by x 0 exponential of minus at. So if we take the inverse of this, we find x0 exponential of at. That is precisely the expression that we got when we were considering Mathus model. It's always a good idea when you are considering a more general model to check if you find as a special case the solution of a simpler model. So in this case, I think that the solution should be correct, but in order to verify this, we are going to simulate it and we are going to use Simulink. So what we are going to do next is going to be a short introduction to Simulink, and we try to simulate precisely this model.